Hello everyone, and welcome back to the next video in the Simple Third-Person Platforming series. Today we will be covering wall jumping, as well as making it so that the controls are aligned with the player direction regardless of the pitch of the camera. So right now, if you press up and down while the camera is almost vertical, then the character moves extremely slowly, and that's a problem. But if you go side to side, it tends to be full speed. So let's open up Visual Studio. Right here. There we go. Before we get into stuff, let's do some cleanup. Like right here, we've got my vector.y equals 9001. We don't need that anymore. We know how to get the jump button now. And let's add a space in here just for readability. And alright, I think that's good for now. So first things first, we need to make it so that the character can only jump while they're on the ground, because that's another thing. Right now, the player can just spam the space bar and jump as high as they want. So the question then becomes, how do we make it so that we know if the player is on the ground? MyController.move actually returns something that is called collision flags. So if we start out with collision flags here, if our keyboard's in the right mode, collision flags, we'll just name the variable flags equals MyController.moveMyVector. Flags now contains the information of any collisions that happened in the controller.move thing that we performed. So now that we have this information, we can use it to determine if the character should be able to jump or not. So down here, we're going to use flags to determine if character can jump or not. But we haven't done anything with flags, or the type that this is an enum yet, so we'll save that for a bit later. First, we want to handle the simple stuff. So the way that we're going to check if the character is on the ground, or the way that we're going to make it so that the character can only jump if they're on the ground, is by using another if statement. So we're going to say if the character is on the ground, or if they can jump, then we'll actually execute the jump code right here. And to do that, we will just add another if statement. So if can jump. The variable name is, again, completely arbitrary. So this will be a Boolean value, which is just a true or a false. Now the question becomes, how do we get the information from this flags character to be stored in a bool that can be accessed up here, the next frame? So we're going to have to create a variable outside of the update method right here. So normally we have public in front of here so that we can edit it in the inspector, but this time we just want to be able to store the variable between frames. So we'll say bool can jump and start it off as false. Again, a bool is just a true or false value. And then if can jump, then we actually do the jump stuff right here. So now we have to use the flag to determine if they can jump or not. So somehow, if on ground, set can jump to true, otherwise set can jump to false. And we know the code for doing this already, so we can just do can jump equals true, and down here can jump equals false. So the question becomes, what do we have in like an if statement here to determine if the character can jump or not? And there's a bit of special syntax for this that I will get into a bit later. But for now, if you open up the collision flags thing right here and hit dot, you'll see you've got a couple options here. Above, below, sides, and none. Each one of these corresponds to a certain true or false value that's all stored in the same variable. But it's not as simple as just saying if flags dot something. You see the above and below things don't pop up here. Instead, we have to do something along the lines of if flags and collision flags dot below, because we want to check if they're on the ground, is not equal to 0. Alright, so this is going a bit out there. This is incorporating a lot of new stuff at once. We're going to put this in parentheses just so that it knows these things are part of the same expression. So the AND operator right here. So normally in a true or false statement, AND is true if both of the statements are true. So if statement 1 is true and statement 2 is true, then AND is true. If one of them is false, then the result is false. So if false and true, then it's false. If it's false and false, then it's false. But if it's true and true, then it's true. What the AND operation does right here is just make sure that the flags is only considering the below thing. So the way this works, let's hop into Paint Tool SI here. Get my tablet working. Alright, in computers, true and false values are stored as ones and zeros, where 1 is true, fabulous handwriting, and 0 is false. So if we use the AND operator, so 0 and 1, that equals 0 because we're doing false and true, and because not both of them are true, the answer is false. It's just stored as ones and zeros. That's the only difference. 0 is F, 1 is T. If 1 and 1, then the result is 1. If 0 and 0, then the result is 0. So the way flags work is they have a bunch of ones and zeros that are just lined up in a row. So let's say we have 0, 1, 1, 0. This one might correspond to above. This one might correspond to sides. This might correspond to below, for example. And then this would be, I don't know, we'll just say there's 3 for now. So if we have these stored in one variable, so if this is our flags variable, and we have our collision flags thing that we're comparing against, so we're comparing against collision flags.below, which corresponds to 0, 0, 1, because it is just the below value. And we do an AND operation on each of these. We have 0 and 0. So let's have the result here. 0 and 0, as we saw here, is 0. 0 and 1 is 0. And 1 and 1 is 1. Now we are just considering the below flag. And after that, we can compare it to some value to see if the value is a certain thing. In this case, if we're comparing it to 0, we're seeing if it's not equal to 0. The exclamation point equals thing is the same as like a not equals in standard mathematics. Not equal to 0. 0, 0, 0 equals 0, alright? It doesn't matter how many zeros there are. If it's all zeros, then the result is 0. So we're just making sure that after we do the AND operation, that it is not all zeros. If it is all zeros, then there was no collision right here, if that makes sense. If we look at an alternate case, like let's say we have 1, 1, 0, and again this is above, this is sides, this is below. And we are checking against the below flags right here, which is 0, 0, 1. And we run the AND operation on it. 1 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0. And you'll notice that 0 is oftentimes equal to 0, so it is not equal to 0. And that's what we're checking for right here, is we're just checking to make sure if it's not equal to 0. If it is not equal to 0, then we are allowed to jump. Otherwise, and we do otherwise with the else keyword, otherwise, can jump is false. And that by itself should actually work. So let's hop into Unity after hitting save. Where's Unity? There it is. Wait for it to compile and see what happens. Notice I'm spamming the spacebar and the player cannot continually jump into the heavens. Alright, so next order of business before we counter wall jumping is to make it so that when we move up and down that the character doesn't move slow as snot. So as you see right now, they're just moving very, very slowly. As of this moment, the way we're handling rotating the input is just setting it directly to the rotation of the camera. Instead, what we want to do is make it so that it ignores the pitch of the camera, and instead just takes the general direction that the camera is looking and rotates the input to match that. So right now, let's hop into SI again and create a new layer. Hold on. erase the old one. The way things are currently happening is, say we've got the camera up here, and it's looking down on the player who's right here. Oh, that is a perfect capsule. And the ground's right here. And we've got the input that is, so here's the ground right here. And we've got input that is actually sending them like this, because it's being rotated to match the rotation of the camera. What we want to do instead is just make it so that it is flat on the ground, but matches the orientation that the camera is in. And it's not as straightforward as it might originally seem, however, it's still relatively simple. So we're going to do something called a quaternion .look rotation. There's a lot of fancy words in there. A quaternion is just a thing that stores rotations in Unity. So if we type out quaternion here, let's see, we have a lot of different things available to us. And one of them is, where is it? Look rotation. Look rotation. There we go. Creates a rotation with the specified forwards and upwards. So we just pass in a vector 3, which we're already familiar with, and it will interpret that as the forward direction. And it just makes a rotation that has that forward as the forward of the rotation. So we'll pass in the forward that we want. In this case, we can do camera transform dot forward. Conveniently, transforms have a forward field on them, so we can just easily get the forward direction on the camera. And as an up argument, we just say vector3 dot up. And vector3 dot up is just shorthand for new vector3. Geez, why does it like vector2 so much? 0, 1, 0. So it's just shorthand for that. And then, instead of directly multiplying the camera transform dot rotation by my vector, we want it to multiply it by this instead. So we will create a temporary variable for this. So we'll say quaternion input rotation equals, and this just creates a temporary variable that we will then replace this with, input rotation times my vector. So all we did was replace the camera's actual rotation with our look rotation right here that we create by getting the camera's forward axis. But if we look back at our drawing in Psi here, currently our forward direction is pointing downwards, and we don't want that. We want it to be like this one. So what we're going to want to do is somehow project this directional vector that we have that's pointing down right here, just eliminate any of the verticalness of it. So we've got ground right here, and we want to take this vector as it is right now and instead move it up so that it's now this. We want to exclude any vertical components of it. And the way we do that in code is by using the project on plane method. So right here, rather than just doing a camera transform dot forward, we do vector3 dot project on plane. And thanks to IntelliSense, it says it projects a vector onto the plane defined by a normal orthogonal to the plane. And that's just fancy talk for saying we give it the vector that we want to exclude a direction from, and then we give it the direction that the surface is facing. So in this case, the surface is facing up, so vector3 dot up. Vector3 dot up. There we go. I don't know why it's so difficult typing out vector3. And that should be it. Hit and save. Hopping into Unity. There we go. And let's hit play and see what happens. Notice it now moves up and down much faster now. Perfect. There's no slowness due to the orientation of the camera. It moves the same speed in all directions, except for diagonals. As you'll see, it actually moves a lot faster on diagonals than forward and backwards or side to side alone. And that's actually a glitch that was in a lot of early video games, where you would have people that would look in like a diagonal direction and then hold to the side so that they'd actually run faster. The way that we can fix that, and the reason for that is we're getting our input in each of these axes, so we end up with a vector that looks like it looks like 1, comma 0, comma 1. And if you get the length of that, Pythagorean's theorem, that's about 1.414 square root of 2. And 1.414 is oftentimes greater than 1, which is why we get that increased speed. So what we're going to want to do is actually cut it off so that we have a smaller length on that. Also, just to visualize this, so right now we've got our grid here, and here's our like input direction, and here's 1, and there's 1, and we want to make it so that it always has a length of 1 right here. So we want to chop it off right here so that the vector now has that length. And Unity provides an easy way to do that with the vector3.clampMagnitude method. And save. So my vector right here, my vector equals vector3.clampMagnitude, and we just pass in the existing vector, so my vector, and then it wants a max length that we want, and that'll just be 1. So it will just cut off its magnitude at 1 if it exceeds it. But if it's less than that, like if we've got a controller and we're tilting the analog stick maybe halfway, it's not going to mess with it. It's going to leave it halfway so that we can walk our character instead of run, for example. And if we hop into Unity, after saving of course, and hit play, let's see what happens. So now it has constant move speed in all directions. And perfect! So what you just saw there was the capsule shooting up into the air. That's actually a byproduct of a feature, not a bug, a feature that the Unity character controller has. If we hop into our capsule thing here, let's rename this to character so it's easier to find. My character. Right here we see step offset. What this does is it automatically makes it so that if there's a change in height, the character will automatically step up to it. If we go into our code right now, you'll see the way that we handle vertical velocity is by actually getting myController.velocity.y. So what happens is the character steps up immediately. Like over one frame it will step up however big the step height is. So in that case our step height was like 0.3, so if there was a change in height of 0.3 it would immediately step up by that. That's a huge change in velocity, because it happens over the course of a single frame, which is why we get that slingshot action that shoots it into the air, because it detects it as an immediate change in velocity rather than simply moving the character up. So the way we're going to handle dealing with that is by, instead of accessing the controller's velocity, we're going to have our own variable. So we need a variable that holds our vertical velocity and transfers it between the frames. Well, we've already got a variable named vertical velocity, so why don't we try that? Why don't we try using that vertical velocity instead of the velocity.y? So vertical velocity here, and then instead of declaring the variable right here with the float, we declare it right here, which means that it can be transferred between frames. Float vertical velocity. So what ends up happening, it starts out at 0 and then it begins accelerating down. So we have 0 minus gravity strength times time dot delta time, so that's an acceleration downwards. Then we multiply that by time dot delta time and then use that to move the controller down. But we keep the original value of vertical velocity and then reuse it again here the next frame. So we have our movement downward that we had the previous frame, and then we again subtract gravity strength from it again, which gives us acceleration. So let's save it and hop back into Unity. Alright, and open up our scene. You'll notice a few things are different, and that's because the universe hates me when I'm making these tutorials. Alright, I believe it compiled. And let's move around. And indeed, we no longer have the slingshot action. However, we have a different problem. You'll notice the capsule almost teleports downwards when you go off of the surface. And it's starting to behave somewhat erratically now. And the reason for that, if we hop back into Visual Studio, is vertical velocity is constantly increasing. As I said, it's accelerating every single frame, but we have nothing that stops the acceleration, even when it's in contact with the ground. So what we want to do is make it so that we halt all vertical velocity when it's in contact with the ground. And the easiest way to do that is to add something right here. So right here we're actually checking if it is in contact with the ground. And if we add some braces around this, then we can add more lines to the body of this if statement like we do up here. How we have multiple lines inside this if statement. Instead of just setting can jump to true here, if it is on the ground, we're also going to set vertical velocity to 0. And hop back into Unity. Hit play. Oh, wrong window. There we go. And now we have the smooth drop off as we walk off the edge again. However, there are still a few quirks. For instance, the bumping as it goes down. It might be difficult to see. Let's zoom in here. See that jumping as it goes down? The easiest way to fix that, it's a bit of a hack fix, but if we set vertical velocity to a negative value here, that will act like sort of sticking the character to the surface. It will push them downwards into the surface even while it's already on the ground, so that when we move towards an angled surface, it will move it down it instead of moving it straight away so that it then drops down back onto the angled surface. So let's hop into Sai here and I can demonstrate this. Where's Sai? There it is. At my graphics tablet. Again, it's blank because the universe hates me. Come on. Alright. So right now we've got an angled surface here. And we've got our capsule. It's a beautiful capsule. And right now we're moving it to the side and then it detects, hey, well, it's airborne now. So then it drops down. So instead what we want to do is have it so we have our capsule. Again, beautiful. And we always have some downwards component that's forcing it downwards that gets added to our input, so we end up with this diagonal downward movement that kind of moves us down the slope at the same time. So back in Visual Studio here, let's just set this to a negative value. So we'll say -3. The amount isn't really important as long as it sticks it to the surface. And not back into Unity. Save. Where's save? Oh, derp. Alright, so now we don't have the hoppy motion as it goes down the surface of the ramp. Alright, and for the last part of this video, we're going to make it so the character can wall jump a little bit. Not full wall jumping ability, or rather too full in fact, because the player will be able to wall jump indefinitely. Rather than simply checking if the player is on the ground right here, let's also check if they're on the wall. And we've got other collision flags for that, being collision flags.sides. But how do we incorporate that into this? Well, with what we know so far, we would also be able to create a separate if statement that says if flags and collision flags.sides. However, we can also incorporate them into the same statement by doing this. Collision flags dot sides, or the pipe symbol means or collision flags dot below is not equal to 0. So what is this doing? If we hop back into Sai, let's create a new layer. So originally we have our collision flags, which let's say is 1, 0, 1, and this is above, sides, and below. And we were checking against collision flags.below, which is this, and we were doing an and, so 1, 0, 0, 0, 0, 0, 1, 1, 1. Instead, what we're going to do here is have our flags, which let's say is 1, 0, 1. Then we're going to do an OR operation on collision flags.below, which is 0, 0, 1. And collision flags.sides, which in this case would be 0, 1, 0, or returns true if either of the operands are true. So if either of the two is 1, then it's 1. That sounded confusing. But for example here, 0 and 0, 0, 0 and 1 is 1, and 1 and 0 is 1. So this is the new thing we're going to be doing our AND operation against, is 0, 1, 1. So it combines just the sides, the sides and the bottom, and it checks against both of them and makes sure that after you do the AND operation with them, it is not equal to 0. So if it's either connected to the sides or it's connected below, then we will do the stuff in here. So let's hit save, hop back into Unity, and hit play and see what happens. We should be able to wall jump indefinitely now. Our keyboard's in the right mode anyways. Oh, notice how it kind of jerks upwards a slight amount. And that's because we're setting our vertical velocity to a negative value if it's on the wall. So what happens is we're like, alright, we can jump now, but it stays in contact with the wall, so it immediately goes down again because we're setting its vertical velocity downwards. But theoretically, if you did a frame perfect input to get away from the wall, you should be able to. Hold on, let's give our camera a bit of a better angle here. Game object align with view. And hit play. If you move away from the wall on the frame that you hit space, you should be able to actually do a wall jump. Let's see if I can do it. Yeah, there you go. So there you go. There was a wall jump. And you see if I spam the space bar, it doesn't normally work. However, that's not really our desired effect. We don't want the player to have to do an input accurate to the 60th of a second, nor do we want it so that the player can just wall jump infinitely up one wall like this, just by spamming the space bar. So, in the next video, we will rectify that, as well as make it so that our momentum is retained upon jumping. So right now, we can move away and then instantly move back. There's no sense of like momentum or inertia or anything. And if we walk off an edge, we can just instantly drop down if we release the input. So we'll be taking care of both those issues in the next video, and until then, thanks for watching.